Hey folks, in this video we're going to go through section 5.4. It's one of the shorter ones. It talks about weight versus mass. So, weight versus mass. Okay, this is a key distinction. I think most of you got this, but it's really important to be sure. Weight is a force, and mass is a measure of inertia. So, the weight is the force that's a result of a body pulling on another body due to gravity. Your weight's going to change depending on what planet you're on. And it's going to change depending on your distance from the center of the Earth. But your mass will never change. You can be weightless, but you can't be massless. Right? So, the force due to gravity F sub g is the mass times the acceleration due to gravity, which we usually just write as mg. So W equals mg is the relationship that we will typically use. And this is always directed toward the center of the Earth. And if not the Earth, then whatever, the center of whatever mass we're talking about. Okay. So, key points. Weight. Weight is extrinsic. It depends on external factors. So, its value depends on external factors. For example, the pull of gravity. Okay, so weight measures the pull of gravity on a body. Mass is intrinsic, internal. It is not dependent on external forces or external circumstances. So its value is independent of external factors. Mass measures internal resistance to a change in motion. The more mass, the harder it is to change the motion of something. All right, so just to work with these a little bit, let's take an example problem. A man weighs 900 newtons on Earth. Okay, so this is weight. Newtons is a force. You can't say a man weighs a certain number of kilograms because that's mass. You can say a man has a mass of however many 200 kilograms or whatever. Okay, so find the weight on Jupiter. Okay, where the gravity of Jupiter is 25.6 meters per second squared. Remember, gravity of Earth is 9.81 meters per second squared. Okay, so you're going to expect the weight to be about 2.5, 3 times more, right? So first, find mass on using the weight on Earth. All right, so weight on Earth equals mass times g of Earth. So 900 newtons equals the mass times 9.81 meters per second squared. So we end up with a mass of 91.7 kilograms. Okay, so we got the mass on Earth. Now, since mass doesn't change, we can find the weight on Jupiter pretty easy. So the weight on Jupiter is going to equal the mass, because that doesn't change, times gravity of Jupiter. So weight on Jupiter is the mass, 91.7 kilograms, times g of Jupiter, which is 25.6 meters per second squared. So weight on Jupiter is 2,349 newtons. Okay. One more. Another example. A woman weighs 120 pounds. Now, pound is a force measurement. Okay. Find her weight in newtons and mass in kilograms. All right, so her weight is force, 120 pounds, times the conversion between newtons and pounds. Between the two forces, they're 4.448 newtons on a pound. So the weight in newtons, okay, is going to equal 533.8 newtons. Remember I said earlier that a newton is roughly a quarter of a pound, slightly less than that. Okay, so that's the weight in newtons, and since weight equals mass times g, mass is weight over g, the algebraic manipulation. So the weight in newtons is up here, 533.8 over 9.81 meters per second squared. So mass in kilograms is 54.4 kilograms. Just a little aside here on G. So G of the Earth, 9.81 meters per second squared in metric. G of Earth is also about 32.2 feet per second squared. So if you're doing something in English or customary units. Okay? So that's section 5.4. See you next time.